Close your eyes for a moment and imagine yourself standing at the edge of a shore that is not of water, but of space. Behind you is Earth, soft, familiar, lit with the gentle pulse of oceans and cities. Ahead lies the night, deep, cold, and filled with a patient scatter of distant suns. When we speak of traveling to the stars, we are talking about moving across distances that stretch imagination across light years where time and silence hold court. Interstellar travel is not a mere prolongation of our voyages to the moon or Mars. It is an invitation to leave the cozy scale of planetary life and enter a different kind of time, one where journeys are measured in decades or centuries, and where motion itself becomes a meditation. Tonight, we will walk that slow path together. We will ask, how might we move between the stars? What machines could carry us or our messages? What are the dreams that have guided scientists for generations? And what are the stubborn realities that keep many of those dreams at the horizon for now? The story of interstellar travel blends physics, engineering, imagination, and economics, but it is also a tale of quiet persistence. Human beings have always reached outward, across rivers, across oceans, across continents. Interstellar travel is simply the next horizon. It will be slower, more careful, and more reflective. When you listen, let the thought of distance settle gently in your mind. Imagine planning a voyage that takes generations, or one so small that it hurls a tiny sunlight-driven chip across the dark to arrive as a whisper in another system. Both possibilities sit on the table of our future. Both demand patience, care, and an acceptance that moving among the stars is a slow art. In this way, thinking about interstellar travel becomes a quiet exercise in humility. We learn to make plans that outlast our lifetimes, to love projects that will be tended by people we will never meet. Let that stretch of time be comforting rather than frightening. We are beginning a long conversation with the cosmos. Before thinking about engines and sails, we must sit with the scale itself. The nearest star system beyond our sun is about 4 light-years away. That means light, the fastest messenger in the universe, takes 4 years to travel from one star to the other. At speeds achieved by our fastest spacecraft today, reaching that star would take many tens of thousands of years. That simple reality has shaped every idea about going to the stars. Distance is the master constraint. It tells us what is feasible, what will remain a thought experiment, and how we must think differently about travel that spans generations. There are 2 broad responses to the tyranny of distance. One is to move the ship extremely fast, near a significant fraction of light speed, so that the journey finishes in a human lifetime, or at least within a few decades. The other is to accept slow motion, building durable vessels or sending messages and tiny probes that cross the gulf over centuries. Each approach brings trade-offs. high speed requires enormous energy and exquisite shielding. Particles of interstellar gas and dust strike protons and small grains at relativistic velocities and can cause catastrophic damage to anything unprotected. Slow travel requires patience, life support systems that can last generations, and social systems that can sustain a mission over centuries. Then there are sidesteps, trick solutions that change the rules. Concepts like wormholes or warp fields would, if possible, short-circuit distance itself. But current physics makes these ideas speculative, mathematically intriguing, and tightly constrained by energy and causality questions. Until proven otherwise, the comfortable, practical lines of thought remain: how to design propulsion systems that give us the most speed for the least energy, and how to design tiny, clever probes that can survive a long, lonely crossing. As you breathe slowly, consider this. Traveling between stars is not merely an engineering challenge. It is a project in patience, a test of how well a civilization can plan beyond the span of an individual life. It asks us to commit resources, imagination, and hope to projects that may only realize their purpose long after we are gone. In that extended perspective, interstellar travel becomes not just a technological goal, but a cultural one, a way to bind generations into a shared dream. One of the oldest ideas for getting humans to other stars is the so-called generational ship, a self-sufficient vessel so large and well-organized that whole communities could live aboard it for decades or centuries until they reached a distant world. Imagine a city ship, nested layers of habitat, gardens, schools, and workshops, spinning gently to provide artificial gravity. In the best stories, such ships become microcosms of civilization, carrying forward knowledge, culture, and the steady rhythms of daily life as they drift between the stars. The practical challenges are many. Life support must recycle air, water, and nutrients with extraordinary reliability. Mental health and social dynamics require attention. Confining thousands of people in an enclosed world for generations would test psychology in new ways. Food systems must be resilient. Disease prevention and medical care must be planned for long horizons. There are also ethical questions. Who decides to go? Who will be born aboard, and what consent did they have? These questions place a moral weight on generational voyages that is absent from robotic missions. Technologies can ease some burdens. Advances in closed-loop life support, hydroponic farming, and radiation shielding can make habitats more sustainable. Nuclear power, if politically possible, offers long-lived energy. But the energy required to accelerate a city-sized mass to even a few % of light speed is vast. So most generational ship concepts accept much lower velocities and correspondingly long missions. These projects become social artifacts as much as engineering feats. They test our capacity for long-term planning, for education across centuries, and for building institutions that outlive their founders. So when you picture a generational ship, picture it as a calm, self-contained world where entire human lives unfold in quiet rhythm as the stars drift by outside. It is a vessel of continuity and patience, a reminder that not all voyages must be measured in days or weeks. Some are measured in generations and in the gentle endurance of human community. If we want to bridge interstellar distances within decades rather than centuries, we must turn to speed. One of the most active and elegant ideas of the last decade imagines tiny probes, not heavy ships, pushed by concentrated beams of light. Picture a wafer-thin spacecraft with a reflective sail. A powerful ground or space-based laser array bathes the sail in light so intense that it accelerates the chip to a significant fraction of the speed of light. In principle, a gram-scale probe could cross to the nearest stars in a few decades, returning images and data in a long but humanly comprehensible timescale. This idea, sometimes called a directed energy light sail, has been championed in recent years with formal projects exploring its feasibility. The practicality is both tantalizing and honest, building lasers with the required power, focusing them precisely, and protecting fragile microcraft from interstellar particles are hard problems. Interstellar dust grains striking a probe at relativistic speeds can vaporize or shatter it. Engineers must design protective coatings, small cross-sections, and possibly sacrificial shielding to let even tiny missions survive. Yet the small probe approach changes the economy of interstellar travel. Rather than asking for a single colossal craft, we can imagine fleets of tiny scouts, each one cheap enough to risk loss, each one sending home a faint, precious signal. In such a future, exploration becomes distributed. A slow bloom of light-launched chips crossing dark space, each a messenger that says, "We were here." There is quiet poetry in that vision. Small, fragile instruments sampling distant suns, bringing back the first whispers of alien systems. The concept also invites humility. These probes would not return people, only data. But their technology might be the first step to a more ambitious future, where phased lasers and larger sails push ever heavier cargo. For now, the appeal lies in the achievable. Small steps across an enormous night. Another family of ideas reaches for engines that store enormous energy in compact form. Nuclear propulsion has long been a dream for deep space travel. There are two broad types: high-efficiency nuclear thermal or electric propulsion that can help within the solar system, and more exotic high-energy concepts aimed at the stars. The mid-range approach, nuclear thermal rockets and nuclear electric systems, are attractive for fast missions through our solar system and for launching heavy payloads to the edge of interstellar space. NASA and research institutions continue to study nuclear thermal systems because they offer much better performance than chemical rockets for long trips. For true interstellar ambitions, engineers have imagined controlled fusion rockets, engines that fuse light nuclei to release massive energy and propel a vehicle at high speeds. Projects inspired by classic studies like Daedalus and its later successor concept Icarus explored designs for multi-stage fusion probes capable of reaching a significant fraction of light speed. Though such designs remain theoretical and enormously challenging, fusion offers the tantalizing prospect of sustained, high specific impulse, a way to accelerate heavy payloads far beyond what chemical rockets can manage. There is, too, the radical idea of nuclear pulse propulsion envisioned in historical programs like Project Orion. That concept proposed propelling a craft by detonating a sequence of nuclear charges behind it, converting explosions into push. In the mid-20th century, engineers produced detailed studies showing that enormous mass fractions and high accelerations could be achieved this way, though political, environmental, and legal obstacles have kept such designs grounded for now. Today, discussions of pulse propulsion are largely academic, but they serve as useful thought experiments. If humanity could manage the political will, the engineering is not entirely beyond comprehension. These nuclear concepts share an important quality. They treat energy density as the key constraint. The farther and faster we want to travel, the more compactly we must store and release energy. Fusion is elegant on paper, but the technological path is steep. Nuclear thermal systems are nearer term and may be stepping stones toward grander ambitions. In all cases, careful, patient research and responsible policy must accompany technical development so that the dream of stellar motion proceeds with both wisdom and safety. Even if we solve the propulsion problem, the medium between stars is not empty in the practical sense. Tiny atoms, charged particles, and microscopic dust grains fill interstellar space. At slow speeds, these particles pose negligible trouble, but at relativistic velocities, a sizable fraction of light speed, even a single grain, becomes a projectile capable of shredding a probe. Models of relativistic impacts show that a stream of small collisions can erode protective materials and degrade electronics over the long duration of a crossing. That realization forces engineers to think carefully about shielding, redundancy, and risk tolerance. Radiation is another companion. Cosmic rays, high-energy particles born in supernovae, and other energetic events permeate space. Spacecraft traveling between stars would be constantly bombarded. For human missions, this is an existential hazard. Prolonged exposure to cosmic radiation increases cancer risk and damages tissue. For robotic missions, electronics and sensors must be hardened and often duplicated. The design of long-lived probes must account for cumulative degradation and the possibility of partial failure. Then comes the navigation problem. Guiding a craft across light years requires exquisite precision. Small deviations at launch can translate into enormous offsets at arrival. Without the ability to make large mid-course corrections, probes must be built with both accuracy and a capacity for small, precise maneuvers. For laser-launched microprobes, these constraints are complicated by the fact that they may be traveling so fast that any course correction is hugely costly. All these problems are solvable in principle, but they are not trivial. Engineers explore clever workarounds, sacrificial shields that vaporize in front of a probe to absorb impacts, slender geometries that minimize frontal area, distributed swarms where losing some fraction of probes still yields mission success. The path forward is not a single silver bullet, but a portfolio of strategies that reduce risk and accept that any interstellar mission will take place in an environment that is both silent and merciless. There is a romantic and compelling category of ideas that tries to have its cake and eat it, to enable journeys faster than light without violating the fundamental local speed limit set by relativity. The most famous of these is the Alcubierre warp concept, a solution of Einstein's field equations that, in theory, allows a bubble of space-time to move such that a craft inside experiences a short trip between distant points. The craft itself remains locally stationary, while space is contracted in front and expanded behind. For decades, this remained a mathematical curiosity, mainly because early analyses demanded negative energy densities and exotic matter. Recent theoretical work, however, has found more general solutions and suggested that some of the previously prohibitive requirements may be softened, though not eliminated. These remain speculative areas of physics and mathematics. Wormholes, another speculative idea, would be tunnels connecting distant regions of space-time. Both concepts raise issues about causality, enormous energy requirements, and the unknown physics of stabilizing such structures. The reason these ideas persist is not purely fanciful. They push the limits of our understanding, and they show where physics might evolve in the far future. For now, they belong to a special class, beautiful, mathematically interesting, and distant from practical engineering. But the history of science shows that speculative math sometimes predicts real phenomena decades later. So thinking about warp fields and wormholes keeps the imagination open and helps drive theoretical advances that may reshape our future thinking. In practice, the future of interstellar travel will likely be a patchwork of techniques, each serving different goals. Shorter-range nuclear, electric, or thermal systems will make our solar system far more accessible, enabling staging, resource extraction, and the construction of infrastructure in cislunar and interplanetary space. Those near-term developments will provide test beds for more ambitious systems and create the industrial base needed for larger endeavors. Directed energy launchers and light sails may deliver the first interstellar data in the coming decades if investments continue. Fleets of small probes could be the initial scouts, returning the first pictures of other systems and their planets. In parallel, incremental advances in fusion research could yield engines that eventually push larger payloads over long timescales, and nuclear propulsion research could increase the speed and reach of heavy spacecraft. Each technology informs the others. Microprobe sensors, ruggedized electronics, and compact power sources developed for laser sails will help fusion probes and vice versa. There are organizational lessons too. Interstellar projects will require multinational, multi-decadal cooperation and possibly funding models that accept long yields. The breakthrough initiatives, academic consortiums, and national agencies each play complementary roles. Visionary goals, deep study, and near-term testing respectively. In short, the road to the stars will likely be many small, carefully tested advances stacked together rather than a single, sudden leap. As you imagine this patchwork, picture a tapestry, threads of laser technology, nuclear know-how, materials science, and quiet political will woven across decades. Each small breakthrough is a stitch. Over generations, the tapestry may become a bridge across the dark. Beyond the physics and engineering lies the human question: should we go, and how do we decide? Interstellar missions will require tremendous resources. They will require societal consensus to commit funds and attention to long projects whose benefits may be cultural rather than immediate. There are also ethical considerations. Generational ships pose questions about the rights of those born into voyages they did not choose. Robotic missions raise concerns about planetary protection, the responsibility to avoid contaminating distant worlds and corrupting potential biospheres. Economically, interstellar missions seem impractical if judged on short-term return. but they can be justified as investments in knowledge, technology, and inspiration. Programs like Apollo reshaped industry and education in ways that were unforeseeable at the outset. Interstellar programs might similarly drive new technologies. Philosophically, the attempt to reach other stars is a sign of maturity, a civilization that plans across centuries and cares enough about the future to seed it with projects beyond immediate profit. There is also a cultural value in the act itself. To aim for the stars is to assert a long-view mindset, to plant dreams that define a civilization's aspiration. When we choose to fund and pursue such endeavors, we teach future generations to think beyond narrow time horizons and to treat the planet and our shared destiny with a kind of generous stewardship. So as you rest in this thought, consider the deeper reward. A species that reaches for the stars not out of conquest, but out of curiosity, humility, and a wish to connect across time. That wish, more than any engine, propels us forward. As we come to the close of this gentle exploration, let your mind return to the small blue planet behind you. Earth, with its slow weather and quick tides, remains our home. The idea of traveling between the stars can be grand, frightening, and deeply calm all at once. Grand in scale, frightening in the obstacles, calm in the patient project of taking one careful step after another. We have crossed the map of possibilities tonight. Generational ships that cradle human life across centuries. Tiny, laser-launched scouts that brave particle clouds and return image whispers. Nuclear and fusion concepts that imagine stronger pushes, and speculative warp dynamics that stretch the imagination. We have listened to the constraints, dust in interstellar space, the tyranny of distance, the challenges of long-term life support, and we have also listened to the promise that human curiosity applied patiently can reach astonishing places. The future of interstellar travel may not arrive in our lifetimes, but the stories, the plans, the prototypes, and the papers are how civilizations prepare to be more than a single generation. They are acts of faith in time itself, investments in the centuries to come. If you allow the idea to settle warmly within you, it becomes less a question of technology and more a meditation on care for knowledge, for the future generations who will tend these missions, and for the kindness that must guide us as we reach outward. So breathe slowly now. Imagine a tiny probe crossing dark space like a luminous thought. Imagine a ship where children read under artificial starlight, dreaming of the worlds they will never see. Imagine physics and poetry braided together, a culture patient enough to plan the impossible. The cosmos waits, distant and gentle. The future of interstellar travel is not only about how we move, It is about how we choose to be, patient, curious, and kind across the long night.